All right, we're into lesson 3 now, problems involving motion. So this is where we're going to take advantage of those differential equations and antiderivatives we've learned and apply them to some problems. They may or may not involve motion. Who can really say? So recall that the derivative of position gives us velocity, and the derivative of velocity gives us acceleration. So the antiderivative of acceleration is going to be velocity. In other words, v of t plus c, right? Antiderivatives, we're always going to have those constants. And the antiderivative of velocity will give us position, or s of t plus c. All right, let's jump into an example. Example 1. A particle moves in a straight line with an acceleration in centimeters per second squared, defined as a of t is equal to 6t plus 4. If the point's initial velocity, okay, so our initial velocity is negative 6 centimeters per second, and our initial position is 9 centimeters. We want to determine our s of t and find its displacement in the first minute. Okay, well, that's a lot to do, so let's break this down slow. First off, we're given acceleration, and eventually we want to get to position. So we know we're going to be having to work backwards, do some antiderivatives. But first, let's do one antiderivative at a time. Let's not move too quickly here. So our first antiderivative from acceleration will give us velocity. So v of t, it's a bit of a weird v, I'll own that one. V of t is going to be equal to the antiderivative of a of t with respect to t. Okay, which in this case is going to be the antiderivative of 6t plus 4, which, using our antiderivative skills, we can tell that this is going to be 6 over 2 t squared plus 4t plus c, or 3t squared plus 4t plus c. Okay, but here's the thing. We are told that the initial velocity, so that means the velocity at our initial position, is negative 6 centimeters per second. So what we can do is we can say that v of 0, v when t equals 0, at the initial time, is equal to negative 6. That is just from the conditions that we were given in the question. So using that, we can say that negative 6 is equal to 3 times 0 squared plus 4 times 0 plus c1. I'm going to call this c1. I've changed my mind. It's not just c, it's c1 now. Which means that c1 is equal to negative 6, if we solve that out, and therefore the expression for our velocity is going to be 3t squared plus 4t minus 6. Okay, so we've got one piece of our puzzle figured out, the velocity. But really, that's not what this question is asking for. It's asking for position. So to get to position, we know s of t will be the antiderivative of v of t with respect to t. So that means s of t is going to be equal to the antiderivative of that was a little ugly, of 3t squared plus 4t minus 6 dt, which means s of t is going to be, well, this is going to be 3t cubed over 3 plus 4t squared over 2 minus 6t plus another constant. So we simplify this, we get t cubed plus 2t squared minus 6t plus c2. Okay, but as you might imagine, now we need to solve for c2. But hey, we've been given another initial condition, that the initial position is 9 centimeters. So when t is 0, our initial position, when t is 0, we know that our position is 9. So that means that 9 is equal to 0 cubed plus 2 times 0 squared minus 6 times 0 plus our C2, which means C2 is equal to 9, which gives us our position equation, which is what we were looking for, at least one of the things we're looking for, which is t cubed plus 2t squared minus 6t plus 9. All right, so we've got the equation for our position. And make that 6 look nicer. That's the equation for our position. That's just using the same strategy that we used in differential equations. Now, there is one last thing we need to do. We've determined ST, that's great, but now we also need to find the displacement, which is change in position, in the first minute. So displacement is the total change in position compared to our starting point. So displacement in the first minute, well, that is just going to be our position at 60 seconds minus our position at 0 seconds. That's going to be our displacement. So to solve that, all we have to do is take our position formula and take it at both points. So we have that S of 60 is going to be 60 cubed. That was a bad bracket. 60 cubed plus 2 times 60 squared minus 6 times 60 plus 9. And that S of 0 is just going to be, well, we know all of those t's are just going to get canceled out, and it's just 9. So S of 60, so I'll just call this our displacement. Our displacement is just going to be the subtraction of those two things. So our displacement, when we subtract those out, the 9s are going to cancel delightfully, right? That's really nice. So what we'll be left with when we subtract those is 60 cubed is that. 2 times 60 squared is 7,200, and 6 times 60 is 360. The 9s cancel out when we subtract. And what that leaves us with is 222,840. So the total displacement over the first minute is 222,840 centimeters, or if you prefer, 2,228.4 meters. There we go. So that is how we can do a motion problem using differential equations. You know, it seems like a lot, but honestly, if you break it down step by step, it's all pretty simple. There's nothing really complex in there compared to what we've done in the past, at least. All right, let's look at try 1. Try it yourself, then you can come back and check my solution. So we're given that the acceleration of an object is defined by the equation a of t is equal to cos t minus 2 sine t, with s of 0 being 0 and v of 0 being 5. We're determining the equation of the position. So we start off with our a of t, meaning to solve for v of t, we're going to take the antiderivative, the most general antiderivative of a of t dt. So this is going to be equal to the antiderivative of cos t minus 2 sine t, which dt, don't forget my dt, which is going to be sine t plus 2 cosine t plus some constant c1. Now, we have ourselves an initial condition. V of 0 is equal to 5. So we can set that 5 is equal to sine of 0 plus 2 times cosine of 0 plus our c1. That's coming from our initial condition there. I just apparently got real lazy with my highlighter. I can be better. I'll be better, I promise. All right, so when we solve for that, that means 5 is equal to 0 plus 2 times 1 plus c1. which means C1 is equal to 3. Therefore, we have that V of t is equal to sine of t plus 2 cosine of t plus 3. So that's our V of t. So to get S of t, we need to take the antiderivative of V of t, the most general antiderivative of V of t, dt. So this means that S of t is going to, of course, be the antiderivative of sine t plus 2 cosine of, that's not how you write cosine, 2 cosine of t plus 3 dt, which gives us negative cosine of t plus 2 sine of t plus 3t plus some constant I'm calling C2. Now, again, we have ourselves an initial condition. We know that S of 0 is 0. So what this gives me is that this is negative cosine of 0 plus 2 sine of 0 plus 3 times 0 plus C2 is all equal to 0. That's from our initial condition. So we solve this out. 0 is equal to, well, cosine of 0 is 1, so this is negative 1, plus 2 times sine of 0 is 0, plus 3 times 0 is 0, plus C2. And we get that C2, when we solve that out, is equal to 1. Therefore, our position formula, S of t, is going to be negative cosine of t plus 2 sine t plus 3t plus 1. Oh, I just barely have enough room for that. And there we go. All right. 2 more examples to go through for this lesson. Example 2. A ball is tossed downwards from a height of 100 meters with an initial velocity of 10 meters per second. How long will it take the ball to hit the ground? So I'm just gonna draw a sketch first. When I'm given like these kinds of things, it's nice sometimes to just draw what it looks like. So I've got this like situation here where I'm starting at 100 meters, and then I'm throwing the ball, I'm tossing it downward towards the ground from 100. So this is my h of t, and this is t. I don't know why that looks like not a t, but it's supposed to be. That's t. So we're told that we have an initial velocity of 10 meters per second as it's being thrown downwards. And it wants to know how long will it take the ball to hit the ground. Okay, so keep in mind, hit the ground, that is when h of t equals 0. It hit the ground when the height is 0. So to do this, the first thing I need to establish is I need some kind of numbers to work with to help me out here. And you know, if I'm talking about something falling downwards, well, we're given an initial velocity of 10 meters per second. But we got to take acceleration into account, because you might throw the ball and give it an initial velocity, but if it's falling downwards, we all know the acceleration that's acting on it, that's gravity. So a of t is equal to negative 9.81, but I'll just do 9.8 meters per second. 9.8 is good enough. So that means that the velocity that that ball is traveling at is going to be negative 9.8 t, because I'm taking the antiderivative of acceleration, plus some constant. So I just take my antiderivative. So now that I've taken the antiderivative and I've got my velocity, I know that v of 0 is equal to 10. So that means that 10 is equal to negative 9.8 times 0 plus some constant, C1. Do my calculations, and I get C1 must be 10. So not very difficult calculations, to be fair, but hey, I still did them. That counts. It's important. I made an effort. Celebrate me. Honestly, I'm just killing time while I'm writing out this equation. I apologize. All right, so that's my v of t equation. All right. So now that we've got our velocity, we need to figure out our height. Now, height has basically taken the position. Oh, that's funny. I'm sorry, I started laughing before I said the punchline, but that's because I didn't intend to make it a punchline. It just happened. So the joke is that position, oh dang it, I ruined it already. Height takes the position of position in this question. I'm just going to move on, shall I? Okay, so h of t is going to be in place of our position, and so that means it is the antiderivative of v of t, dt. So our antiderivative, I should say, that's going to be the antiderivative of negative 9.8 t minus 10 Why am I putting a box around this? I am losing my grip with reality, folks. I blame, who knows? I mean, we all know what to blame, right? No, you're probably just blaming me. Fair. All right, so this is going to be equal to negative 9.8 t squared over 2 minus 10t plus c2, which reduces to negative 4.9 t squared minus 10t plus c2. So we want to solve for C2, but again, we have initial condition. We're wanting to know when it hits the ground. And it hits the ground. 3, 2, 1. So we need to solve for C2, but we do have an initial condition. We know that when time is 0, we're at 100 meters above the ground. So we can say that that h of 0 is equal to 100. Therefore, 100 is equal to negative 4.9, 0 squared, minus 10 times 0, plus C2, which obviously means that C2 is 100. Hooray, for easy math, which gives us our h of t. Negative 4.9 t squared, minus 10t, plus 100. Beautiful. Which also, if you think about it as an equation, makes a lot of sense. That's going to be our y-intercept, so clearly the constant had to be 100 since this is a quadratic. Also, I don't know why that t became a 2. I'm going to make it a t again. Okay, so that's our equation for height, but we want to know when it hits the ground. So it hits the ground when the height is 0. We've already determined that. Hits the ground when h of t equals 0. So what we have is that 0 is equal to negative 4.9 t squared minus 10t plus 100. So to find our t values, I'm just going to bust out the quadratic formula. This is going to be 10 plus or minus the square root of negative 10 squared minus 4 times negative 4.9. That looks like a 9. Now it looks like a 4 times 100. All over 2 times negative 4.9, which simplifies to 10 plus or minus the square root of 2060 all over negative 9.8. Or if we're lame and we want to bust out calculators, I suppose we could say that that is the same thing as negative 5.7 and 3.6. Now, we know time isn't negative, so we can reject this one. And we can say the ball will hit the ground after 3.6 seconds. Ta-da! All done. Woohoo! It's like we're doing physics. because we are doing physics. That's usually what applications of math end up being. It's often physics. So, one more example. A stone is tossed upward with a velocity of 8 meters per second from the edge of a cliff 63 meters high. How long will it take the stone to hit the ground at the foot of the cliff? Okay, so in this case, so again, I'm going to just sketch this out. So we're starting at a cliff that, I forgot that I changed this. I changed this and I forgot to change it in here. I changed it to 100. Why? Don't question it. I just did. So it's 100 that we're starting at. And we're tossing it up this time. So it's a little different. We have to deal with it a little differently. We're tossing it up and then it's going to come back down. Obviously, unless it's somehow magic, in which case calculus probably doesn't apply. So we're tossing it up with an initial velocity of 8 meters per second. Okay? We want to know when does it hit the ground. Well, again, this is a very similar process. Everything's more or less the same as it was in the last problem. We still have a of t being equal to negative 9.8 meters per second squared, which means very nicely for us that a lot of things line up to be very similar throughout the problem. For example, the antiderivative v of t is exactly the same as the last one, negative 9.8 t plus some constant. Same thing. The only thing that's going to change is what that constant is. This time, though, our initial velocity, we have that v of t0 is equal to 8 this time. So that means that 8 is equal to negative 9.8 t plus c1, where t is, of course, 0. And what that tells us is that c1 is 8. And so the equation for our velocity, v of t, is negative 9.8 t plus 8. Okay, so we've got our v of t. Now, just like before, we can get our h of t by taking the antiderivative, right? Remember, h of t, my pen's not working. Hold on, there it is, it's back. Remember, h of t is going to be the antiderivative of v of t. So what we get is that h of t, very similar to the last equation we had for h of t, is going to be negative 4.9 t squared. I'm honestly pulling that out from our previous equation because the only thing that's different from the previous question is the constant. So I can just kind of skip a few steps here because it's the same as the previous problem. Plus, this time instead of 10t, it's going to be 8t plus some new constant, c2. But we know that at time 0, hey, it's 100 again. So we have that this is negative 4.9 times 0 squared plus 8 times 0 plus c2. So c2 is equal to 100. And just like before, we see that, again, our c2 is just our y-intercept. Negative 4.9 t squared plus 8t plus 100. It's just a quadratic, right? This is very similar to Math 20-1 in terms of dealing with parabolic travel. So we again can solve for t when h is equal to 0. So hits ground when h of t is equal to 0. So we're trying to solve for when h of t is equal to 0. So we have 0 is equal to negative 4.9 t squared plus 8t plus 100, which means we can yet again bust out the handy-dandy quadratic formula. This is going to be negative 8 plus or minus the square root of 8 squared minus 4 times negative 4.9 times 100. This is all very familiar. Unless, of course, you didn't watch the previous example, in which case, if you get confused, go watch the previous example. It's almost exactly the same as this one. So when we finish this off, we get t is equal to negative 8 plus or minus square root of 2024, all over negative 9.8, I'm going to be honest, I don't love that, so I'm just going to cancel those negatives. Yes, technically I have to cancel a negative here too, but plus or minus divided by negative is also plus or minus, so I don't have to change that one. And that gives me two values of t, again, if I want to be lame and use a calculator, negative 3.8 and 5.4. Again, we can reject the negative time, and we get that the stone hits the ground after 5.4 seconds. All right, and there we go. That's problems involving motion. Go do some homework and enjoy some physics. Bye.